We will now talk about separable spaces. A topological space is separable if it has a countable dense set. Okay, so we have the following proposition. So V Banach, if V star is separable, then V is also separable. Okay, so proof. So let Fn n equals 1 to infinity be a countable dense set in V star. Okay, so you choose xn in V such that you have norm xn equal to 1 and fn of xn is greater than 1/2 of norm fn. This is possible because norm fn is nothing but the supremum of fn of x over norm x equal to 1. So definitely you can find an xn with norm x equal to 1, xn equal to 1 such that it is bigger than this. So we will assume for simplicity that the base field is R, otherwise you argue only with the real and imaginary parts, whatever we do now. Okay, so now let us assume, so W be the space generated by the xn. So these are the set of all finite linear combinations of xn. Okay, so then W0 is finite rational linear combinations of the xn's. So W is the set of all, is a space generated by xn, that means these are all finite linear combinations. Now we are taking finite linear but with rational coefficients. So then W0 is dense because you are taking finite rationals are countable and you are taking finite linear combinations of xn, which is also a countable set, and therefore this is W0 is countable and dense in W. So sufficient to show W is dense in V, because every element in V can be approximated by W, which element in W, which in turn can be approximated by something in W0. So W0 will be dense in V and W0 is countable. So this will prove that you have a countable dense set and therefore it is separable. Okay, so let us assume, so the Hahn-Banach method, so let us assume f in V star such that f vanishes on W. So to show f equal to 0. Okay, so fn's are dense, therefore there exists an fm such that norm f minus fm will be less than epsilon. Okay, and now f of xn is 0 for all n, because f vanishes on W, W is generated by the xn's, and therefore in particular f of xn is 0 for all n, and therefore 1/2 of norm fm is less than fm of xm, which is, I can write as fm minus f of xm. Okay, and that is less than or equal to norm of fm minus f into norm xm, which is 1, and that is less than epsilon. Therefore norm fm is less than 2 epsilon, and therefore norm f is less than or equal to norm of f minus fm plus norm fm, which is less than 3 epsilon. Epsilon is arbitrary, so this implies that f has to be 0. So this proves that if V star is separable, then V is separable. So now let us, the converse, so example, converse not true. You take L1, L1 is separable because you take all finite sequences, that is, which are 0 after a finite stage, that is dense in L1 because of the norm, and we have seen this already. And then if you take finite rational sequences, they are the countable set which will be dense in the whole space. So L1 is separable. In fact, all LPs other than L infinity is separable. So L1 separable, L1 star is L infinity, but L infinity is not separable. In fact, when trying to prove L infinity star is not L1, we even showed, came across this fact that finite sequences are not dense in L infinity. But L infinity is not separable. Let us take any Fn countable set in L infinity. Okay. Now define F in the following fashion. So Fi is equal to 0 if mod Fii is bigger than or equal to 1, and 2 if mod Fii is less than 1. Then obviously F belongs to L infinity. And what is norm F minus Fi? Well, at the ith coordinate, the distance is certainly bigger than 1, and therefore this has to be bigger than or equal to 1 for all I. For all I or for all I. Okay, so sorry, no, it's not Fi here, it is Fi. Okay, so this shows that no countable set can be dense in L infinity. So L infinity is not dense, but C0 star is L1, so C0 star equals L1, so this implies that C0 is separable, but this you can check directly, you can produce a countable dense set. In fact, again, finite sequences with rational coordinates, this will be automatically a countable dense set. Okay, corollary. Okay, V Banach. So V is separable and reflexive if and only if V star is separable and reflexive. Okay, so proof. So V star separable and reflexive implies that V is separable and reflexive. Because if V star is separable, V is separable. If V star is reflexive, V is reflexive. We know all this. Okay, so now we assume that V is separable and reflexive. So the point is L1 is not reflexive. That's why this we have a counter example here. This under proof, if you like, that L1 is not reflexive. If V is separable and reflexive, then this implies J equals V double star, which is isometrically J of V, which is V double star, is automatically reflexive and separable. And therefore, this implies that V star is separable. And of course, V reflexive implies V star is reflexive, and therefore V star is also. So V reflexive implies V star reflexive. Therefore, you have all these things. So we have that it's same. Okay. So now we have a very important theorem. V Banach, then V is separable if and only if the weak star topology on B star, this is the closed unit ball in V star, is metrizable. That means you take, if V is separable if and only if, what is the condition? You take B star, the closed unit ball in B star, and you put the weak star topology restricted to B star, then it is equivalent to a metric topology. There exists a metric whose topology is the same as the weak star topology restricted to B star. So it's essentially a metric space. Okay, so proof. So we are going to first assume that V is separable. Then you can have a countable dense set. So countable dense set. So without loss of generality, we can assume xn not equal to 0 for all n. Why is this so? So if you take, if suppose 0 is in that countable dense set, take any neighborhood of 0, then if you take any ball which does not contain the origin, because of density there will be a xn here. Okay, so every neighborhood of 0 will also contain a point from the will contain a non-zero element of the xn's, and therefore the non-zero, and therefore given any open set, you, even if you have 0, if it intersects 0, then it will also have to intersect a non-zero element. So it is enough to assume that you have that all the elements are non-zero. Okay, so now you define, so for f in B star and g, f and g in B star, you define d of fg. This is the definition. Okay, sigma n equals 1 to infinity 1 by 2 power n into norm xn. That's why I wanted all the xn's to be non-zero, and then mod f minus g xn. Okay, so this is the definition. So why is this well defined? Because if you take d of fg is less than or equal to sigma 1 by 2 power n norm xn, norm of f minus g norm xn, and therefore that cancels, and this is less than or equal to norm of f minus g into sigma 1 by 2 power n, which is 1, and therefore it's a convergent geometric series. So this is finite. Okay, so this is well defined for all f and g, and it's easy to check that it's a norm, it's non-negative, that's clear. If it is 0, then f and g agree on xn, which is a dense set, therefore they have to agree everywhere. So f equals g, and conversely also triangle inequality is trivial, it just comes from the triangle inequality of the modulus, and therefore we have that this is a metric. So dfg is a metric. Okay, so now we want to show that this metric topology is equivalent to the weak star topology in the thing. So let us take a weak star neighborhood. So let f naught belong to B star and U a weak star neighborhood of f naught in B star. What does it mean? So U will be of the form set of all f in B star such that mod f minus f naught xi, sorry, yi is less than epsilon, 1 less than equal to I less than equal to k, and then you have yi in B for 1 less than equal to I less than equal to k. So this is how a weak star neighborhood will look like. Okay, so let R be positive. Okay, then by the density for every I there exists xni such that norm yi minus xni is less than r by less than epsilon by 4. So so epsilon is given here. Okay, so then choose R. So this is for each 1 less than equal to I less than equal to k. Now choose R such that R into 2 to the n power 2 power ni norm xni is less than epsilon by 2 for all 1 less than equal to I less than equal to k. Now let F belong to B D, that is the ball with respect to the metric, center F naught and radius R. Okay, then for all 1 less than equal to I less than equal to k, we have mod F minus F naught of yi, which is less than equal to norm mod F minus F naught yi minus xni plus mod F minus F naught xni. Okay, now the first one is less than or equal to F minus F naught in norm, each of them is in B star, so the norm is less than 1, so F minus F naught is less than 2. yi minus xni we have chosen to be less than epsilon by 4 plus mod F minus F naught xni. Now what is that? That is connected to the definition. So if you have f of x, this one term in the infinite series here, so F minus F naught xni will be less than or equal to dfg, which is less than r, into 2 power ni x norm xni. So from the definition of the thing, it will be 2 power ni r into 2 power ni norm xni, and that we have chosen to be less than epsilon by 2. So this is equal to epsilon by 2 plus epsilon by 2 equal to epsilon, and this implies that f belongs to U. Therefore BD F naught R is contained in U. So what have we proved? That every weak star open set contains a ball in the metric space. Therefore every weak star open set is open for the metric topology. So now for the converse. So now we have to take any ball and show that it is also weak star open. So let us consider a ball B D F naught R, and consider the weak star neighborhood of F naught given by U epsilon k equal to set of all F in B star such that F minus F naught modulus xi by norm xi is less than epsilon 1 less than equal to I less than equal to k. So this xi's are from the countable dense set which we already have. Okay. Now I am going to choose epsilon to be less than r by 2 and k such that sigma n equals k plus 1 to infinity 1 by 2 power n, which is 1 by 2 power k, and that I want to be less than r by 4. Okay. So if f belongs to u epsilon k, where epsilon and k have been chosen in this fashion, what is d of f naught? This is equal to sigma n equals 1 to k 1 by 2 power n norm xn and mod f minus f naught xn plus sigma n equals k plus 1 to infinity 1 by 2 power n mod x norm xn into mod f minus f naught x. So the first one you have norm, this we already saw, f minus f naught xn by norm xn is less than norm of f minus d into 1 by 2 power k. So this is less than or equal to 2 times 1 by 2 power n, which I will take instead of k, I will take all the way to infinity, whatever may be k, and therefore this is less than 2 times, then f minus f naught x power n is less than epsilon, and therefore x minus f naught xn by norm xn is less than epsilon, and therefore this is epsilon which is less than r by 2, so this is less than r by 2. Okay, so let me explain that. So mod f minus f naught xn by norm xn is less than epsilon, and therefore that will come out. So you will just get 1 by 2 power n 1 to k, which is I can take less than 1 to infinity, and consequently I will get this is less than just epsilon, and epsilon is less than r by 2, plus the remaining thing f minus f naught x power n by norm xn, that will be just the norm of f minus f naught, which is less than or equal to 2, plus sigma 1 by 2 power n k plus 1 to infinity, that is r by 4. So that is 2 times r by 4. So r by 2 plus r by 2, which is less than r. So this is strictly less than. Okay. And therefore you have u epsilon k is contained in BD f naught r. So every weak star open, so weak star open, metric open, implies weak star open. Okay, so this proves that the metric and weak star topologies are the same if the space is separable. So now conversely, assume weak star topology is metrizable. Then to show V has a countable dense set. Okay. So for each n, consider the ball, center origin and radius 1 by n. So this is a ball in a metric space, and that is the same as the weak star open thing. Then this ball contains a weak star open neighborhood. So un, so there exists un contained in BD 0 1 by n, and un is a weak star neighborhood of the origin. So this is set of all f in B star such that mod fx is less than some epsilon n, and for all x in some phi n. So phi n contained in V is a finite set. So now you take D equal to V union phi n. So D is countable. So E, all finite rational linear combinations from D is also countable. And E is dense in the space generated by D. That is, all linear combinations of elements from D, that's a subspace, E is dense in it. So suffices to show D is, so the space that the space generated by D is dense in B. So you take f in V star. So fx equal to 0 for all x in the space generated by D. Then if f of x is 0 for all x, in particular it is 0 for all x in phi n, and therefore you have f belongs to un for all n. Therefore f belongs to intersection un, n equals 1 to infinity, which is contained in the intersection b0 1 by n, n equals 1 to infinity d, and that is nothing but singleton 0, and therefore f equal to 0. So this proves by, therefore, the space that is, so that is V is separable, because E is a countable set and that is dense in D, in the space generated by D, which in turn is dense in whole space V. Okay.